Hello, in this video I'm going to go through some circular motion questions. We'll see how many we can fit in and we'll carry on over a few more videos. Right, so we start with a jet engine, jet aircraft even, preparing for takeoff along a horizontal runway. The engine is running but the brakes are applied. Right, so the jet is not yet moving. Draw an arrow to show each of the following forces acting on the jet. So we got the weight. Right, nice easy starter. That's always going to be vertically downwards. The force produced by the engine, which is going to be horizontally in the opposite direction. You know, the engine's firing out the back, so the jet's going to be moving forwards. That's what the point of the engine is. It's driving the jet forwards, or at least when it starts moving, it will. And the total force exerted by the runway on the jet. Right, this is an interesting one that sometimes these sort of things catch people out because they get confused as to what the brakes are doing here. So let's think of the difference between the engine and the brakes. So the engine is not self-contained to the jet. It is firing material out of the back of the jet, and it is, you know, making the jet move forwards. All other forces being removed. So it's a driving force for the jet, but the jet isn't then a completely closed system. You know, if you think of the discussions we've had about closed systems, that means you've got nothing leaving that system. But clearly we have with the engine because it's blasting stuff out of the back. The brakes, however, are entirely internal to the jet. All they're doing is stopping the wheels from turning around. So if you thought you had a jet which just had fixed wheels, so the wheels could never turn, so there were no brakes because they were just rigid, then well, that's taking away the effects from the brake. It's just an internal setup of the plane, and you can't have an internal force which is going to stop the external motion of an object. So the brakes in themselves don't stop the plane from moving. All they're doing is stopping the wheels from turning, which means we're going to have the friction on the ground is going to stop the plane from sliding. You know, if the wheels can turn, the plane will roll. If the wheels can't turn, the plane has to skid in order to move. So you're getting that friction effect going on there. But the brake force is internal to the plane. So it can't be the thing that's stopping it from moving. Right, the long and the short of it and all of this is, well, we have got friction then acting between the plane and the ground because the wheels are locked in place by the brakes, but we've still got this driving force, this T force from the engine, which is trying to push the plane off to the left here. The only thing that is stopping that is the friction against the ground, and the fact that the plane would have to skid rather than roll. So we do have friction on the ground, which means the total force exerted by the runway on the jet must be at an angle. It's a combination of the reaction force, which is going straight up, and the friction, which is going horizontally to the right. So we've got those two, and then the resultant of that is going to be our F going off at an angle. So yeah, you need to be able to think through with forces as to whether they're internal or external in their behavior. So the engine is external, it's pushing stuff outside of the jet, whereas the brakes are internal, so they can't be affecting the motion, at least stopping the motion in itself. So yeah, hopefully that makes that part a little bit clearer. The brakes are then released. The maximum force produced by the engine is 28 kilonewtons. Takeoff speed is 56 meters per second, and the mass of the jet is that. Right, calculate the minimum distance the jet travels. Right, okay, people approach this in different ways. You get some do the F equals ma and then assume that. I mean, you can do that, it's fine. I find it a little bit lazy. I'd rather use physics skills of saying, well, the work done is both the energy transferred and it is the force times the distance. So we've got the energy transferred to the plane must be half mv squared, it must be the kinetic energy that's coming from the engine. So we're building up that amount of kinetic energy by applying a particular force, 28 kilonewtons, through a particular distance. So we've got a half times 6200 times 56 squared is equal to 28,000 D. I just think this is better physics. Right, let's keep away from the calculator, seeing as they've given us some nice numbers. So we take off a couple of zeros on either side. I'm going to halve one of the 56s to make a 28, which I can then cancel on this side to give a 10. So our D is going to be equal to 62 times 56 divided by 10. So what have we got when we multiply all of this together? We've got 3,000 plus 360 plus 100 plus 12, all divided by 10. So let's get rid of a load of zeros and make that a 1.2, which gives us 347.2, which is 350 meters to two significant figures. Yeah, it's nice when they give you friendly numbers like that. Explain why the runway needs to be longer than the distance calculated in this first part of the question. Well, there's going to be work done against losses. So this is going to be friction and air resistance. So we're not just going to be transferring all of our energy into kinetic energy here. There's going to be other bits. It's going to be losses plus a half mv squared is equal to 28,000 D. So that's where it's going to be going. So if we've got this extra bit on here, then the D will go up. So that's what's going on with that bit. Right, now the jet is in the air. It's flying in a horizontal circle, radius r, constant speed of 86 meters per second, and it's doing this by tilting 35 degrees. It's saying there to the horizontal, but clearly that's to the vertical. So yeah, they've made a mess up there in the question. With the jet flying in this way, there's two forces. Okay, so show the magnitude of the force L is about 74 kilonewtons. Right, well, resolving vertically, there's going to be no net force. So we've got the L cos 35 degrees is equal to the weight, which is 6200 G. So let's just stick all of that into the calculator. 6200 times 9.81 divided by cos 35 is 74500. So 250, sorry, 74250 newtons, which is 74 kilonewtons to two significant figures. And then they want the radius. So the radius is doing our usual F equals ma, but for circular motion, because we know that A is v squared over r, because they've given us v. So we'll stick with that rather than go into the r omega squared version. So we look at this linear speed here rather than an angular speed. So what we're trying to work out, we're trying to work out r, right? So we've got that 74,250 sine 35 degrees, that's our F. We need to divide that by our mass, 6200, divide that by our v squared, so 86 was it squared, and that is 1 over r, so we just have to take the reciprocal with that at the end. So multiply that by sine 35, divide by 6200, divide by 86 squared, and then do 1 over the answer, 1.1 kilometers. So r equals 1077 meters, 1.1 kilometers, again to two significant figures. There we go. So I think the interesting part of that is that bit right at the beginning with what's going on with the brakes and why have we got this then force, this resultant force F here going off at an angle. So I think that's the key part to take from all of this. Okay, it turns out there's another part to this question that I hadn't noticed, so we carry on. We're now flying in a vertical circle, doing a loop-the-loop. So we've got some stuff that we need to say about this. So for a certain speed, the pilot can experience a sensation of weightlessness. Okay, at a particular point along the path, we've got to mark where that is on the path. Right, this gets us into some interesting points, because the term weightlessness is really horrible. I mean, that's why they've got here a sensation of weightlessness, because of course the sensation of weightlessness doesn't mean that you've got no weight. It means that we're in free fall. We've got no reaction force which is counteracting the weight. That's what we're used to feeling. We've always got our weight acting downwards towards the earth, towards the center of the earth, but usually we've got a reaction force which stops this, and that's what we're feeling. When you take that away and we're just falling, we're just in free fall, then it gives us this sensation of weightlessness, but obviously we do still have weight. So that's what makes this term a little bit awkward. That's why in some parts of the world people they use a different definition of what weight is. They go for an operational definition of weight rather than a theoretical one. So in the theoretical sense, we're saying, well, weight is the force due to gravity. Whereas the operational definition is going to say, well, weight is what we measure on a set of scales. In which case, if we're in free fall with scales underneath us, well, it doesn't record anything because the scales are falling with us. Everything is falling. We record nothing on the scales at that time. It's only when the scales are then fixed that we get a reaction force and we measure what the weight is. So that fits in with this idea of being weightless. If you take this operational definition of what the scales are measuring. From a theoretical definition, well, it doesn't really make any difference if we've got a reaction force or not. We've still got the weight W sitting there. Nothing has changed. So we know from experience that we get this sensation when we're at the top. So we can label that as A. Why is this the case? Well, we need to have this constant centripetal force all the way around here because we're moving at a constant speed. So if we're at the bottom, we've always got weight acting downwards. If we're at the bottom, we have to have a strong reaction force going upwards in order to give our centripetal force. At the top, the weight is sufficient in order to do this. So we don't need any other forces. It's like we're in free fall because the only force acting upon us is the weight acting downwards. They haven't asked for an explanation because it's quite hard to describe it all quickly. So they've just asked us to mark the point at the top, but that's what's going on. In order to get a centripetal force, we only need the weight when we're at the top. Right, the next bit. State the magnitude of the vertical component of the contact force exerted by the seat on the pilot at A. Right, well, yeah, that's going to be 0. So again, we just have to state it. We've just been through all of that of what's going on here. We've just got the weight acting downwards. We haven't got anything else acting downwards. There's no reaction force going upwards. So that's going to be 0. Right, next part. In this maneuver, it's convenient to analyse the motion of the jet in terms of two forces. Constant weight W and a variable force P. P is the resultant of the engine thrust, the lift from the wings and the air resistance. Okay. At the point B, the jet is flying vertically upwards. Explain why the force P is not directed towards the center of the circular path. Right, okay, so they've set this up as if they were going to ask something really, really horrible, but fortunately haven't. Right, so when we're at B, they've told us there's only two forces, right? So if we're at B, then we've got our plane, we've got the weight acting downwards, we've got P, wherever P may be, but the resultant force must be acting towards the center of the circle. So this is two sides of our force triangle. We know that's the resultant. We know that is our weight. So therefore, this must be the direction of P. So the resultant is equal to P plus W. And just drawing out that triangle shows that P must be acting upwards and to the right. Therefore, P must act up and right. So that's why it's going in that direction. So drawing out that force diagram is pretty useful. You can do it in two steps. Yeah, you can do the first bit, maybe draw out the weight and the resultant, then say that that the resultant is P plus W, and then you can just draw in that line afterwards. So draw two force diagrams, one with P and one without P. All right, so yeah, that was an epic question. That might have taken up the whole video. I wasn't expecting it to be quite that long.